All right, so welcome everybody. We're going to talk about chapter 6 today. We're going to review the exam results hopefully on Thursday. I have some time tomorrow. Hopefully that time stays time that I have. I think this time tends to get whisked away for various reasons, department meetings and things. I do have a department meeting tomorrow, so hopefully nothing crazy happens with that. But then I should be able to finish grading those exams and we can talk about it on Thursday. Okay. And today we are going to start chapter 6. Let me look at the schedule here and see what we got to do in chapter 6. We're not going to cover all of chapter 6, but we're going to go through section 6.1 through 6.5, and you can see that on the course schedule if you go look that up in the course materials. And so this is all about a very interesting part of multivariable calculus called vector fields. And it has a lot of interesting physical applications. So if there's no questions, let's see if there's a question here. Is there partial credit for the show work exercises on the exam? I assume you're referring to. Yes, that's the point. So I want to look through your work and I'll definitely give you partial credit. So it's not just whether you got the answer. So even if you got the answer wrong on the My Open Math part of the exam, if you showed your work and it looks close, then I can give you points for that. And like I wrote on the exam, the work is worth substantially more than the answer itself. So, any other questions? Okay, not seeing anything, but I'll keep my eye on the chat, see if anything comes up. So, what I want to do is I want to talk about section 6.1, vector fields. Okay, so I'm going to switch over to the camera. All right. So let me just adjust the lighting here. I think it's better if I do this. Okay. All right. So this is section 6.1. Vector fields. And a vector field is just a function. That's all it is. It's just a different kind of function than the one that we've been looking at up till now. Let's just go through the different kinds of functions that we've seen. We've seen real valued functions, right? We've seen real valued functions. So this is something like, f of x equals x squared. And this is what you looked at in Calc 1, right? Just, it takes a real number and it spits out a real number. In this case, the real number is x, it spits out the number x squared. We also looked at real valued functions of more than one variable. So we looked at something like f of xy equals maybe x squared times y, right? So now it's a function of two variables, but it spits out a real number as an answer. So that means it's a real valued function. It's the value that you get when you plug in things is just a real number. And you can do 3 coordinates as well. Something like this. That defines a plane. The graph of that would be a plane. So these are all examples of real valued functions. We also talked about vector valued functions. And so an example of that would be something like r of t equals cosine t sine t. That actually defines a circle. So we're inputting a real number and we're getting out a vector. right? And so if you look at the points that this traces out, we've talked about this function a number of times. This when you plot the points, you get a circle. And you can do more than just 2 coordinates in the output, right? You could do t, cosine t, sine t, something like this. That makes a spiral. We talked about that before. So here's a vector valued function. Now a vector field, what it's going to do is it's going to be kind of, it's kind of like this, but it's going to take more than one input. And so instead of having the input be a parameter, something that just determines where we are on the plot of the function, the input is actually going to be a point in space. And so the input's going to be a point in space, and the output's going to be a vector. And so what we're going to end up doing is assigning a vector to every point in space. That's how we think about a vector field. All right, so that's what these vector fields are. A vector field is a function that takes a point, so you're going to feed in 2 coordinates, and it's going to spit out a vector. All right, so there's going to be a vector here, and it'll also be 2 coordinates. Now, the first coordinate is given as a function of x and y. So we'll have p of x of y. And the second coordinate is going to be a function of x and y. So we have q of x of y. All right, so this guy, I'm going to put a vector sign above him because his output is a vector. I'm not going to put vector symbols above these because their outputs are real numbers. All right, so these are real valued functions. These are like this. All right, p and q are like the f up here. They take 2 real numbers and they spit out a real number. So these guys here are real valued functions. Sometimes we write scalar valued functions to be more precise, because its output is a scalar, not a vector, right? But when you put them next to each other with commas and the vector brackets, that means that the output is actually a vector. Okay, so what we're doing with these is the input here is x comma y, so it's any point in 2-dimensional space. All right. Now the output is a vector. So assigned to this point is going to be some vector. That's the vector that I'm calling PQ, right? PQ. But I'm doing this for every single point in space. So over there I've got a vector, over here I've got a vector, at this point I've got a vector, over here I've got a vector, over here I've got a vector, everywhere. For every single point, I can't possibly draw them all, but for every single point, you can imagine there's a vector assigned to that point. Okay. So let's look at some examples. Okay. So some examples of vector fields. Example number 1 will be the function. Let's just look at a very simple one. We're going to do x over 4, y over 4. Okay, so this is my function p. It's a function of 2 variables, but its output only involves 1. And here's my function q. Again, it's a function of 2 variables, but its output only involves 1. So function p is constant in the y variable. Function q is constant in the x variable. And the question is, what would this look like? Well, if I plotted the vectors that are associated with this vector function, let's start with the point 1, 1. All right, so if I go over here to the point 1, 1, okay, well, the output's going to be, I'm plugging in 1 for x and 1 for y, so my output is 1/4, 1/4. So that's a diagonal vector like this. If I go to the point 1, 0, well, now x is 1 and y is 0. If I plug those numbers in here, I get the vector 1/4, 0/4. So 1/4, 0. So that's the vector that points 1/4 in the x direction, but not in the y. And if I go to the point 0, 1, so now I'm plugging in 0 for x and 1 for y, I get 0, 1/4. So that's the vector that points up like this. And if I go to the point -1, 1, well, now I have -1/4, 1/4. So that's the vector that points like this. And you can see, if you keep going around here and plotting these vectors, you'll get a picture that starts to look something like this. Now, what if I go to the 0 vector in the center, the origin, 0, 0? Well, 0, 0, I have 0 divided by 4, 0 divided by 4. It's just a 0 vector. So no vector there. What if I go out to a vector like a point 2, 2 out here? Well, now I'm plugging in 2 for x and 2 for y. So now I get the vector 1/2, 1/2. So it's a little bit longer. And so the vectors get longer as I go out. And so at every point, I'm going to be assigning a vector. I can just keep going through here and doing this. And you fill up the space with a whole bunch of different vectors. And that is a picture, it's a discretized picture. I'm not seeing the value at every point. I'm only seeing a value at a discrete set of points. But it's a picture of what the vector field looks like. And so this is how we think of a vector field. Now, we're plotting the vector field. I'm not saying, I'm trying to be careful not to use the word graph, because technically it's not a graph. A graph is actually where you have the domain, well, I guess, well, maybe it is a graph. Never mind. I forget what I was saying. The graph has a domain, and then you have, usually on the graph, you have a domain on one axis and the range on another axis, or the domain in a plane and the range on another axis coming out. And so in that sense, it's a little bit different because we're using the same, the domain and the range, we're using the same plane, and we're putting both on the same picture. And so in that sense, it's not really like a graph because we're not using a separate axis or a separate plane to plot the domain on. We're kind of merging them together, right? So yeah, in that sense, it kind of is a little bit different than the graph. So that's why I'm using the word plot. We're just plotting what this vector field looks like at every point. We can look at, let's look at some other examples here. Oh, there's a question here. Does this result in effectively unlimited vectors? Yes, yes, that's true. There is a vector for every point, right? I can take any point over here, and I can get a vector out of it. So you have to imagine that this is filled up with a vector at every single point in space, which is impossible to draw, right? But you can imagine that that's what's going on. And the general idea here is that the vectors are getting longer as I get further away from the center. Let's look at another one. Let's just change things around a little bit. Let's look at, I'll do G, and I think I forgot to put the arrow on the top of the F. I probably should have done that before. It's a vector field, so I should put a little arrow to denote that. You don't have to do that, but it's good to do that so that the reader knows what to expect out of that function. Okay, so here's another one. I'm going to have this one be, let's just switch it around. Let's see what, I wasn't planning on this one, but let's just see what happens if I do, instead of x over 4, y over 4, let's do y over 4, x over 4. Okay. Let's see what we get here. All right. So here my function of x, y here, my p is this one, and my q is this one. All right. So now p is just a function of y alone, and q is a function of x alone. So if I go at the if I go to the origin 0, 0, well, x and y are both 0, so this becomes 0, 0. So this is 0 vector, just like before. If I go to the point 1, 0, well, now x is 1 and y is 0. So now y is 0, so this is 0, and x is 1. So my y coordinate is 1/4. Okay. So because x is 1, the y coordinate of my vector field becomes 1/4. But the x coordinate is 0, right? Because y is 0 there. So it's actually a vector pointing up 1/4 in this direction. If I go to the point 0, 1, so go to this point over here, well, now x is 0, so this coordinate is 0. Y is 1, so this coordinate is 1/4. So my x coordinate is 1/4, and my y coordinate is 0. So I get a vector pointing this way. Okay. What if I go to the point 1, 1? Well, now I'm getting the vector 1/4, 1/4. Well, just like I did before. But you see other things are going on here. If I go to the point 2, 0, so now x is 2, y is 0. Well, now I got y is 0, so I got 0/4. And x is 2, so this becomes 1/2. So I have 0, 1/2. So now it's a little bit bigger vector pointing in this direction. My vectors aren't quite to scale, but I need to draw them at a size that we can see them. If I go 0, 2, so now x is 0, y is 2. Y is 2, so this becomes 1/2. So my x coordinate's 1/2. And so x was 0, so my y coordinate becomes 0 here. So I get a vector like this. What happens if we go down here? What if we go to 0, x is 0, y is -1? Well, now I have the vector -1/4, 0. So that's this vector. And if I go to the point -1, 0, so x is -1, y is 0. Well, I get the point 0, -1/4. So I get this vector over here. And if we keep going with this, you'll see I get a vector like this, and a vector like this, like this. What's happening over here? If I go to -1, 1, so x is -1, y is 1. Well, now I have 1/4, -1/4. Right? So now I'm pointing down this way. That's kind of different. If I go to the vector -1, 2, so x is -1, y is 2, I get 1/2, -1/4. Right? So 1/2, -1/4. So I'm kind of coming down like this. If I go to the vector -2, 1, so x is -2, y is 1. Now I get the vector 1/4, -1/2. So something like this. And if you keep going with this, you'll see that, let's see what happens here. More like this, and it's going to be more like this. So we get a vector field that looks kind of like this, and more interesting than the last one, right? Instead of just radially spreading outwards, we're getting some kind of twisting going on here. And there's an interesting way to think about how a vector field behaves, and that is to imagine the vector field is representing fluid flow. And that's one of the main applications, that's a major application of vector fields, is describing the flow of a fluid. So if you imagine that we're looking down on a river, and the fluid is, the water is flowing around in this river, here if you dropped a particle into the river and just like a little ping pong ball, and then you could just ask, where is that ball going to go? Well, it's going to follow these vectors because this is the direction of the fluid flow. So this ping pong ball would flow up this way and then over here and then kind of go out this way. If I drop the ping pong ball over here, I dropped it over here instead, now it would flow out this way. If I drop the ping pong ball over here, it would flow out this way. And if I dropped it over here, it would flow this way. So you can see we have these flow lines. And that's an interesting way to think about a vector field. Same thing you could have done over here. If we dropped a ping pong ball over here, well, it's just going to shoot out radially, right? So the ping pong ball is just going to go out in this direction because all the vectors are just pointing out radially. If I put the ping pong ball over here, it's going to go out this direction. So it's just, this vector field is just repelling everything. It's like everything's just shooting out from the center. It's like an explosion, kind of. Except things are actually, if you look at the size of the vectors, they actually grow as I move outwards. So it's like things accelerate as they get further away. So it's like an explosion where things are actually accelerating as they go out. This actually is the way that they say the universe is behaving. They say that as the universe expands, things are actually accelerating further, faster and faster away from each other. So if you thought of these as galaxies, this is what's going on, something like this. The vector field isn't this simple, but it's essentially, this is kind of what's happening. Things are moving apart at an accelerated rate. This is how our universe is understood to be expanding from the data we have so far. And here we have something very different. I didn't change the vector field very much. I just swapped the x and the y, but you can see a very different behavior here. It's more of a, I don't know how to describe what's going on. You can just kind of look at the picture there. Let's look at one more and see what happens if I do this. Let me call this one C of xy. Put my little vector symbol there to denote that it's a vector field. And I'm going to put, I'm going to define this one to be x over 4 negative y over 4. I'm dividing by 4 for a reason. It's because I don't want my vectors to be so large that they overlap each other. In these pictures, if I just wrote x comma negative y, the vectors would be crisscrossing each other and it would be very hard to see the picture. That's the only reason I'm putting a 4 here. It's just to make the picture look a little nicer. And when I draw the picture, I'm not really doing it very accurately to scale. So give me a little bit of lenience there. Let's see what happens. See if you can guess what this is going to look like just by looking at the function before we even plot anything. Well, let's take a look at one of these points. If I take the point at the origin, now x is 0, y is 0, okay, I get the 0 vector. Okay, nothing to plot there. What about the point 1, 0? X is 1, y is 0. Well, here, oh, I got the wrong function. I'm sorry. Let me change this. I wanted to look at something different. Let me make this a y. Oh, how did I mess this up? I was looking at I have my notes here. I looked at the wrong line. Let me look at this one. Minus y, let's do y over 2 actually. Let's just change this. And then x over 2. Sorry about that. I should have drawn pictures next to my notes so I knew what I was going to expect. Yeah, this one looks more like what I wanted. Okay, so here's the vector field I want to look at. The other one's interesting too. I invite you to plot that one too. It's cool. But I want to take a look at this one first. Okay, so what's going to happen here? I'm at the point 1, 0. Okay, so x is 1, y is 0. Okay, so that means that this is 0, and this is 1/2. So my vector is 0, 1/2. So I'm pointing up this way. Now what if I go to the point 0, 1? So now x is 0, y is 1. So that means this is -1/2 and this is 0. So that's this vector over here. Okay. What if I go over here? -1, 0. X is -1, y is 0. Right, so this is 0. This is -1/2. Something like this. What if I go to the point 0, -1? Well, now y is 0. No, x is 0, y is -1. X is 0, y is -1. So this is +1/2, and this is 0. So I get this vector. Okay, let's go to the point 1, 1. Let's go up here. Okay. At 1, 1, I get -1/2, +1/2. So -1/2, +1/2, I'm pointing up like this. If I go to the point -1, 1, okay, x is -1, y is 1. So I get -1/2, -1/2. So I get this point, this vector. If I go here, -1, -1, I'm getting +1/2, -1/2. So something like this. And then when I go here, 1, -1, x is 1, y is -1, I get +1/2, 1/2. So I get this vector. You see what's going on here? We're getting a, keep going here. We're getting, if you imagine dropping a ping pong ball on this one, where would it go? Well, it's just going to spin around, right? This is just a cyclical pattern. So things are just spinning. So this would be the vector field that would maybe correspond to like the orbit of the planet, right? Planet's just spinning around some center. Except that the further we go out, the faster things spin, because the further we go out, the bigger these vectors get. So it's actually more like the spinning of a record, right? Or just put a, you know, or a merry-go-round. You know, you just spin it, and the things that are further out are spinning faster, whereas the things that are closer near the center are spinning slower. And so this is actually just like a merry-go-round here. Okay. So I want to look at some of these vectors on the computer as well, because I think they're kind of neat to see that way when you see all the vectors together. So let me share my screen. Our CalcPlot 3D program that we've been using is very good at making vector fields. One thing I did to make a two-dimensional vector field is in CalcPlot 3D, I went down here and said restrict to 2D, because it can also do three-dimensional vector fields. And we'll take a look at those. All right, but let's focus on 2D for now. So I'm going to restrict to 2D, so I just get this two-dimensional view. And the first vector field we looked at was x over 4, y over 4. All right. So this is a picture of a more complete picture of that vector field that we drew. Okay. It's drawing more of the vectors. Now I'll show you why I put over 4 here. If I didn't put over 4, this is the picture. It's just a little bit harder to see. You can kind of see what's going on when you draw this many vectors, but if you just draw a few, it's kind of harder to see. They start to overlap each other and stuff like that. So if you divide by 4, the only reason I did that is to just make a picture just a little bit more contained, you know. Also, by default, CalcPlot 3D will, because that happens, it will, by default, want to scale the vectors down in length. I've changed that, and I said, no, let's keep the vectors the length that they are. I've already accounted for that in my definition of the vector field. But by default, I think it puts a 4 here, so it'll scale them down even shorter. because it realizes that a lot of times the vectors are going to overlap and it's harder to see. So by default, CalcPlot3D will scale the vectors down and make them shorter than they actually are. But if you want to make them to their realistic length, make that a scale factor of 1, and then you don't have to worry about that. But you may need to adjust this to get a pretty picture. The other vector field we looked at was y/4, x/4. That was the second one we looked at. And that's this guy. We just drew a few of the vectors, but we were seeing this behavior. And so you can see as a particle flows along, it tends to come near this diagonal and then flow out along this diagonal. And if it's down in the bottom part, it flows down this other diagonal going the other direction. So there's these two outwards diagonal, this diagonal where it flows either to the upper right or to the lower left. That's kind of an interesting one. You get that just by swapping the x and the y. And then the last one we did was negative y/2, x/2. So just put a minus in front of the y, essentially. And we get a very different vector field. We get this spinny vector field. And like I said, you can scale the vectors down so that you get a cleaner picture. Right? And you can see that things are just spinning here. There's another program that was designed by a guy. I think this was designed by this guy. He's got a YouTube channel called 3 Blue 1 Brown. It's very, very good. And he explains calculus stuff. He also explains some other interesting mathematical stuff. And he's got this, I don't know how smooth this is coming across in the video, but he's got the program here that will show you the fluid flow corresponding to a vector field. So this is the vector field we were just looking at. And what it's doing is it's showing you the flow of what a fluid would be looking like. I see a chat's coming in. I'm trying to get a picture of the chat, but Zoom is weird. It won't let me view the chat sometimes until I stop sharing. So let's see. I'm going to try it one more time. Okay, let me stop sharing, and then oh, there it is. As soon as I click stop sharing, it shows me the chat, and then it's almost like it's going to work, and then it stops sharing. Yeah, I see. So you skipped from I'm not sure how old this chat was. Oh yeah, you skipped from example 2 to 3. Oh, I see. When I wrote down the examples, I wrote 4. Yeah, I think it's because I was looking at my notes. Yeah, we did examples 1, 2, 4. We'll just live with that. Okay. It's the opposite of smooth right now. Well, if you load it up, I'll put the link on. I'll put the link to that this program that I'm trying to show you on our MyOpenMath, and you'll see it's very smooth, kind of flowing thing here, and you can look at it on your own. I'm going to try showing you a couple other things here. The vector field, the first example that we looked at was, it has a weird notation entering things in here. You'll have to toy around with it to figure it out, but we had x/4 and y/4. That's not the one. Come on, show me the right one. Oh, it doesn't like this. Oh, weird. I thought my notation was fine. Maybe this is not the right vector. I don't know. It's giving me an error here. I'm not sure why. No binary operators. This is a finicky program, so I'm not sure. Okay, let me just get rid of the 4s here. There we go. That's essentially what we were looking at. So this is essentially the first vector field. So you can see it's just radially exploding outwards. This is the flow that we were seeing. And I don't know how well you can see this, but maybe it'll come up better in the video. And then if we look at The second example we looked at was essentially y comma x. I had some divides by 4s in there, but for some reason that's not working out so well with this. So I'll just get rid of those. Oof. Yeah, this is making my computer sluggish. Come on, go back there. Okay, yeah, this is what we were looking at in the second example. This kind of flow. Okay. All right, let me nuke this. This is making my computer slow anyway. So let me go. Oh yeah, no, actually, there's something else I wanted to point out. So hopefully you can see this picture. Let me do this one first. Another example of where vector fields come into play is in looking at magnetism. So magnets create a magnetic field, which is described by a vector field. And this is a picture of a magnet dropped onto, what they do is they call them iron filings. So you just take, you go to a machinist shop where they've been working with iron, and they shave the iron, they do stuff with it, they carve it, and all these little iron filings fall on the floor. And you can just scoop them up and put them in on a glass tray. And then on the other side of the glass tray, you put a magnet. And as you move the magnet around, you can see how the magnetic field affects the iron filings. And that's what looks like what they did here. I think that this looks like a real picture. I'm not 100% sure about that, but this is what you would see in a real picture. You put a magnet down, and the iron filings align themselves along the flow lines of the magnetic field. And so this is a picture of that kind of it's giving us kind of a picture of the vector field where the iron filings are acting like the vectors. And I wish I could do this as a demo in live, but it's kind of cool. You move the magnet around and you can see these iron filings aligning themselves. And if you do two magnets, you can see how these magnetic fields interact. And you can see how these would be representable by vector fields. And there are equations in physics that describe exactly, given the size of the magnet, how powerful it is, exactly, and how many magnets you have, exactly what the formula for this vector field would be. They describe it using differential equations. So you may not get a formula explicitly like how we've been writing it down, but you get a differential equation which you could use to solve. You could solve to get an idea of what the vector field would look like at different points. Let me go back to CalcPlot 3D, and we can also, I just want to point out that we can do things in 3D as well. Okay, so this is that two-dimensional vector field in 3D. That's not very interesting, but I can put a third coordinate here. I don't know, put Y here, and we can start seeing the vector field coming off of the XY. Ooh, that's an interesting one, isn't it? Coming off of the XY plane. And so you can actually define vectors. This is where we need to start scaling our vectors and making them smaller, because when they're long, it starts getting hard to see. I've got it set to only put 4 rows of vectors going up and down. Let me even cut down the number of vectors in the X and Y directions. And let's make it uniform. So you can see that at every point in space, I've defined a vector. It's really kind of hard to see the things clearly with all these vectors together here. Maybe I should plot even fewer of them. So I'll just plot 4 in each direction. And then it's maybe not so easy to see either. Maybe I'll do 6, right? Something like this. So you can see at every point in space there is a vector, right? And so it's telling us to move in a different direction. Something like this would be used to describe fluid in actually within the river, like, because the water is not just flowing on the surface, it's flowing within the river. Also, gravitation, the gravitational field is in 3D. And so the book goes through an example where they describe how to write down the formula for the gravitational vector field that describes exactly the gravitational force that you feel when you go into outer space and you feel yourself attracted to the Earth or the moon or something like that. So you can do all this in 3D as well. And you can extrapolate and then imagine 4 dimensions and things like this. And I invite you to please go into CalcPlot 3D and play around with this and look at the different things that you can come up with here by playing around with these parameters, get an idea of what things look like. All right. Okay. Just a couple other things to talk about. Oh, I hate it when this happens. My right mouse button is not. There we go, it's back. So we talked about vector fields in 3D. Some other things we should talk about. I just want to mention some terminology. There's the idea of a unit vector field. Unit vector field is just a vector field of unit length, right? So it's a vector field, all of whose vectors have length 1. Okay. So how would I make a unit vector field? Well, for instance, if we go back up to this one up here, these clearly do not have length 1, right? But I could fix it so that they do. I could change this vector field and make it a unit vector field. Okay, so let's make C of xy, that guy up there, a unit vector field. How would I do that? Well, I just have to take each of its vectors and divide by its length, right? To make a vector into a unit vector, you just divide by the length of the vector, right? So if I take a vector and divide by its magnitude, this is always unit length, right? So what I'll do is I'll just take my vector field and divide by its magnitude, okay? So what I have to do is find the magnitude of this. So in this case, we're doing C. The magnitude of C is going to be, well, if you remember the formula was the square root of this squared plus this squared, right? So it's going to be y squared over 4 plus x squared over 4. I can pull out the 1/4. 1/4 comes out of the square root as a 1/2, right? So that's 1/2 x squared plus y squared under the square root. And so I can make my vector field a unit vector field by dividing by this, right? So my new vector field would be the vector field that I had before. It would be, it was negative y over 2, but now I'm going to divide by this, right? So, so I'm dividing by 2. So yeah, but look at what's happening here. I'm dividing by 2, and then I'm going to divide by a half. All right, so 2 divided by a half is, sorry, it's 1 over 2, because I'm already dividing by 2, and then I'm dividing by a half, so that's going to make 1 here, right? So, so I really am just going to end up with negative y over the square root of x squared plus y squared, comma, x over the square root of x squared plus y squared. So that's going to be the same vector field, except all the vectors are going to be unit length. And so you can do this with any vector field. You can just rescale. Wherever it's not a 0 vector, you can divide by its length and get a unit vector there. One other thing that we can do with vector fields, or talk about involving vector fields, are gradient fields. These are special kinds of vector fields. And these are very important. Some vector fields are gradient vector fields. Remember what gradient means. The gradient of a function let's just think of a function of 2 variables. The gradient of a function we denote by this this triangle symbol here, the gradient symbol. And the gradient of a function is a vector that points in the steepest uphill direction. And we compute that by taking the x derivative of the function, comma, the y derivative of the function. If the function had 3 variables, we'd do x, y, and z. And that's how we get the gradient of a function. Well, look at what we've just done. We've created a vector field. Because for every point x, y, we can compute the derivatives. So I can view this as a vector field. And a gradient field is a vector field that happens to be the gradient of some function. Okay, so let's just start with actually, before I do this, I want to point out one other thing. This function, when you use a function to take the gradient and produce a vector field, this function is called the potential function. It's called the potential. Okay. So let's just take a function and see what gradient vector field it produces. All right. So let's just start with a function, and this will be our potential function. Our potential. Okay, let's look at f of x, y equals x squared y. What is its corresponding gradient field? Well, I just find its gradient. That's all I have to do, and view that as a vector field. View that as a function at every point that produces that gradient vector. Okay. So the gradient vector field, capital F of xy, with a gradient with a vector symbol here, is going to be the gradient of f of xy. Okay. So that's going to be the x derivative of the function. So if I take the x derivative of this, I get 2xy, comma, the y derivative of the function. So now I'm going to take the y derivative of this. It's x squared. So this is a vector field that is a gradient vector field, and this is its potential function. Now, a question comes up. You might be asking, are all vector fields gradient vector fields? Can I always find a potential function whose gradient gives me that vector field? Okay, well, let's take a look at some. So our goal here in these problems is to find the potential. So let's write it like this: find the potential. Okay, so I'm going to give a vector field, and we're going to see if we can work backwards. We're going to start with this and see if we can find this, the potential function. Okay, so let me try. Let's just try a very simple vector field. We will just do x comma y, the very first example we looked at. Okay, can we find a potential? Remember what that one looked like. It was essentially just this. I just took out the 1/4, all right? Just to make things easier. So it's essentially this. It's just this radially outwards pointing vector field. Is there a function that has these vectors as its gradient at every point? That's what we're asking, okay? So, okay, well, the potential function, if it exists, this is its x derivative, all right? So the x derivative of f has to be x, and the y derivative of f has to be y. Okay. Well, if the x derivative is x, then I can just anti-differentiate to try to find what f is, right? So that means that f must be, well, the antiderivative of x with respect to x is 1/2 x squared. But what I should keep in mind is that I took an x derivative. So any function of y, when I take the x derivative, would have become 0 because y doesn't depend on x, right? So you treat y as a constant when you take the x derivative. So anything that depends on y differentiates to 0. So that could be included here, right? Because if I differentiate it, it'll be 0 and I'll still get to this. So I can add to this any function of y. That's possible. Any function of y, when I take the x derivative of this, I'll get back to this. And so I have to consider that possibility, right? Now what about this guy? Well, I know the y derivative is y, so I know that the function must look like 1/2 y squared. And then in the same thing that we set up here, I could have some other function of x, because when I take the y derivative of a function of x, I get 0. So that would still get me to here. So on the one hand, my function must look like the top line, 1/2 x squared plus g1 of y. And on the other hand, my function must look like the bottom line, 1/2 y squared plus g2 of x. Are these compatible? Well, yeah, they are compatible because g2 of x could be this, and g1 of y could be that. See, if g1 of y is just this, and g2 of x is this, then both these work. So that's my potential function. It's the function where you either read off the top line, where you let g1 be this guy, or you read off the bottom line, where you let g2 be this guy. Either way, you get the same function. The potential is the function 1/2 x squared plus 1/2 y squared. And actually, I can make it a little bit more general because I can actually add a constant here. But if you check it, if you take the gradient of this thing, the derivative with respect to x, all this stuff is constant, so it's gone, and the derivative of that is x. And then when you differentiate with respect to y, all that stuff's constant, so its derivative, it's gone. So the derivative of this is just y. So we really do get this. This guy is the gradient of this guy. And we see that there's more than one potential, because I can add any constant I want, and it'll still be a potential. Okay, let's look at another one. This will be the last example of the day. All right. I want to look at, so we want to find the potential, still same instructions. And I want to look at negative y comma x. This one is, let me see if I can find the notes that we had, is essentially this guy. I just didn't divide by 2. I just don't want these extra constants to come in the way. So let's just do this. It looks essentially the same. It's just that all the vectors are twice as long, right? So we're spinning. We're just spinning around. So the question is there a potential function that has these vectors as its gradient? All right, let's try to see if we can find it. So what I need to find a function whose x derivative is negative y and whose y derivative is x. Okay, because that's what the gradient is. The gradient of x should be this. The derivative in the x direction should be this, and the derivative of the y direction should be this. if this is going to be the gradient of little f? Well, if the x derivative is y, that means that, okay, that means that f must be negative yx, right? Plus some function of y. Right? And if I take the derivative of this with respect to x, well, this guy's 0, so he's gone. And if I take the derivative of this with respect to x, I get negative y, so it works. So that's what f must look like. It must look something like this. On the other hand, f must look something like, let's see, I need the y derivative to be x, so it must be xy plus some function of x. Because when I take the derivative of this with respect to y, this guy is 0, becomes 0. And then this, when I take the derivative with respect to y, I get x. So the function must look like this. So on the one hand, the function must look like this. On the other hand, it must look like this. Are these compatible? Well, now I'm in trouble, right? Before I could just say that, well, this function was this guy, and this function was this guy, and so they work. I just have to let this be that, and this be that. But I can't do that here, because this is a function of y alone, so it can't equal this. And this is a function of x alone, so it can't equal this, because this has a y in it. So I can't do that crisscross equality like I did before. I can't just say this is this and this is that. Moreover, these things aren't the same. If these things were the same, I'd actually be okay, right? If these ended up coming out the same, I could just say, well, these functions are both 0, or both the constants, the same constant, right? But neither of those things are the same, work. These aren't the same, these can't be equal, and these can't be equal. So there's no way the function can both be this and this. So this is impossible. So therefore, the potential function doesn't exist. There is no potential function in this case. So not every vector field has a potential function, but some of them do. Okay. And that is a very important thing we will want to identify in the future. When we have a vector field, it turns out we'll have there's some things you can do with vector fields if you can find their potential function that you maybe can't do if you can't. This is an important property that some vector fields have. And one name we give for these vector fields is that we call them conservative. So a vector field is conservative if it has a potential function. So dealing with, so that's something that we'll try to identify. Is our vector field conservative? And why do they use the word conservative? Well, because it has to do with conservation of energy. If you move around the vector field, your energy should be conserved if it's representing, well, in certain situations, like in physical situations, if we look at magnetism and gravity and things like this, energy ought to be conserved. That's a main property in physics. And so we'd like to know that our vector fields conserve energy, and we'll check that by seeing if they are conservative. They'll have potential functions. If they don't have potential functions, then they're not conservative, and you wouldn't expect them to conserve energy. And I see somebody asked, sorry, I missed that chat there. Could you also have a constant? And I think I answered that. If I didn't, ask again, and I can get back to it. But I think I mentioned that. All right, so that's all we have for today. Just the idea of vector fields. Any questions? Yeah, you'll have an assignment on this. I don't know if it'll be due Sunday. Since I haven't posted it yet, maybe I'll make it due Wednesday. How about that? That way you have a full week to work on it. Other questions? Okay. All right. Thanks for the good questions, guys. And I will see you on Thursday, and we will discuss. I'm really hoping I'll finish grading all the exams. If the meeting doesn't throw anything new my way on Wednesday, if everything goes well, I should be able to finish grading those exams, and we'll discuss those on Thursday. Okay. Oh, tomorrow. I forgot. I keep forgetting we have my other classes don't meet on Wednesday. So yeah, we'll discuss the exams on Thursday, but I'll meet you tomorrow. Yes. See you tomorrow. And we'll discuss section 6.2. Okay. Have a good one, everybody.